Welcome, my friends. Recall that for matrix addition and subtraction to be defined, the dimensions of the matrix must be the same. For matrix multiplication to be defined, the number of columns in the first matrix must be equal to the number of rows in the second matrix. For example, A is a 2 by 3 matrix, as A has 2 rows and 3 columns. B is a 3 by 2 matrix, as B has 3 rows and 2 columns. Matrix multiplication is defined for matrices A and B because the number of columns of A is equal to the number of rows of B. Matrix A has 3 columns and matrix B has 3 rows. Because the number of columns in the matrix A is the same as the number of rows in matrix B, matrix multiplication is defined. An easy way to think about it is that the inner dimensions must match. The resulting matrix will be a matrix that has the outer dimensions, which in this case is a 2 by 2 matrix. Matrix C is a 3 by 3 matrix, and matrix D is a 3 by 1 matrix. The inner dimensions match, 3 and 3, so matrix multiplication is defined for matrices C and D. The resulting matrix will have the outside dimensions, which in this case is a 3 by 1. Matrix E is a 2 by 2 matrix. Matrix F is a 3 by 2 matrix. Since the inner dimensions don't match, we have a 2 and a 3, matrix multiplication is not defined. We cannot multiply matrix E and F together. Okay, let's try actually multiplying some matrices. Say we have the matrices A and B. A is a 2 by 2 matrix, and B is a 2 by 3 matrix, so the inner dimensions match, meaning matrix multiplication is defined. The resulting matrix will be a 2 by 3 matrix, as those are the outer dimensions. What you need to remember for matrix multiplication is that the first matrix listed, you will be considering the rows, and for the second matrix listed, you will need to consider the columns. This is how you do it. For the very first entry, you need to multiply the first row of A by the first column of B. The first row of A contains 4 and 6, and the first column of B contains 2 and 7. So we multiply 4 times 2 and then add that to 6 times 7. I will do the actual addition later. For now, I'm just going to write everything out. Then for the next value, 1 to the right, this is still in the first row, but now this is the second column. So that means take the first row of column A and multiply by the second column of matrix B. We have 4 times 1 plus 6 times 3. Then moving 1 to the right, we are still in the first row, but now we are in the third column. So we must take the first row of A and multiply by the third column of B. This leaves us with 4 times 8 plus 6 times 5. Now we need to move on to the second row. The next value is in the second row, so we need the second row of A, and it is in the first column, so we need to multiply by the first column of B. We have 0 times 2 plus 1 times 7. Moving 1 to the right, we are still in the second row, and now we are in the second column. So we must multiply 0 times 1 and add that to 1 times 3. The last one is in the last row in the last column. So we need to multiply 0 times 8 and add that to 1 times 5. Now we can simplify everything. We have 8 plus 42, which is 50. We have 4 plus 18, which is 22. We have 32 plus 30, which is 62. We have 0 plus 7, which is 7. We have 0 plus 3, which is 3. And we have 0 plus 5, which is 5. This is the matrix A times B. Now, something interesting about matrix multiplication is that it is not commutative, meaning that changing the order that you multiply does make a difference. And some of the time, matrix multiplication won't even be defined in one of the two ways. For example, in the problem we just did, we found A times B, which involved multiplying the 2 by 2 matrix A by the 2 by 3 matrix B. It turns out that you can't even calculate B times A, switching the order, as that would involve multiplying a 2 by 3 matrix by a 2 by 2 matrix. The inner dimensions don't match, so matrix multiplication isn't even defined. That means A times B is not the same as B times A for matrices. Even if matrix multiplication was defined in both directions, the outcome would not necessarily be the same. Squaring a matrix is not the same thing as just squaring each component of the matrix. To square a matrix, you need to multiply the matrix by itself. For example, if we have this matrix A, then A squared could be found by multiplying this matrix by itself. It's helpful for me to write out the matrix a second time to see what I'm doing. Since A is a 2 by 2 matrix, and we are multiplying A by itself, the result will also be a 2 by 2 matrix, as the outer dimensions are 2 by 2. Remember that you need to associate the rows with the first matrix and the columns with the second matrix. That means we need to multiply the first row of the first matrix with the first column of the second matrix together to get our first number. We have 2 times 2 plus 0 times negative 3. Then we have the first row and second column. So we take the first row of the first matrix and multiply by the second column of the second matrix. We get 2 times 0 plus 0 times 3. Then we have the second row, first column. We have negative 3 times 2 plus 3 times negative 3. Finally, we have the last row, last column. We get negative 3 times 0 plus 3 times 3. Simplifying, we have 4 plus 0, which is 4, 0 plus 0, which is 0, negative 6 plus negative 9, which is negative 15, and 0 plus 9, which is 9. A squared is equal to the matrix with the components 4, 0, negative 15, and 9. Let's try a slightly different problem involving matrix multiplication. Say we have the matrix x, y, 1, negative 6, which is being multiplied by the matrix 1, 3, 4, negative 5, which is equal to 12, 2, negative 23, 33. And we want to solve for x and y. Let's perform the matrix multiplication on the left-hand side. Since we are multiplying two 2 by 2 matrices, the result will also be a 2 by 2 matrix. For the first component, we have x times 1 plus y times 4. Then we have x times 3 plus y times negative 5. Then we have 1 times 1 plus negative 6 times 4. Then we have 1 times 3 plus negative 6 times negative 5. Simplifying, we have x plus 4y, 3x minus 5y, 1 minus 24, which is negative 23, and 3 plus 30, which is 33. Our second row matches the result, which is a good sign. Now, we know that x plus 4y must be equal to 12, and 3x minus 5y must be equal to 2. So we can set up a system, which is x plus 4y is equal to 12, and 3x minus 5y is equal to 2. Now we can use substitution or elimination to solve this. I'm going to use substitution. If I subtract 4y from the first equation, I have x is equal to 12 minus 4y. Now I can substitute this expression into the second equation. I have 3 times 12 minus 4y minus 5y is equal to 2. Distributing the 3, I have 36 minus 12y minus 5y is equal to 2. Combining the y terms, I have 36 minus 17y is equal to 2. Subtracting 36 from both sides, I have negative 17y is equal to negative 34. Dividing each side by negative 17, I have y is equal to 2. Now I can plug this back into either equation to find x. I'm going to use the first equation. I have x plus 4 times 2 is equal to 12. That means that x plus 8 is equal to 12. Subtracting 8 from both sides, I get x is equal to 4. That means the solution is x equals 4 and y equals 2. Alright my friends, that wraps up our video on multiplying matrices.